In this video, we're going to go ahead and try to build another tool that we can use to help us when trying to determine the limit of a sequence. Here's what we have. This theorem states that if it is the case that the limit of a sub n is equal to L as n goes towards infinity, and the function f is continuous at the value of L, then I can go ahead and perform the following manipulation. This is kind of an interesting one here. Take a look at what I have. What I'm going to be trying to compute is a limit of an a sub n that is plugged inside of another function. And what this theorem is going to allow me to do is to say that if I know what the limit of the inside function is, and I know that the function f is a continuous one, then I can actually do the following manipulation. I can let my limit bypass that continuous function, and I can focus on doing the limit of the inside first. If the limit of that inside is equal to L, then as long as my function is continuous at L, I have an answer. Now to kind of see how this works, take a look down here. We see that we have a function that is like a cosine with another thing plugged into it. For the sake of simplicity, let me go ahead and relabel this sequence as b sub n. Okay, I want to find if b sub n is convergent or divergent. Well, using what I know about the theorem up above, I can say that we see that my a sub n would be 2 over n, and f, or in this case I'll say like f of x, is equal to the cosine of x. Right? That's what I have. And so I can clearly say that since cosine of x is a continuous function, notice it's actually continuous everywhere, even beyond just this value of L. Or that is, whatever the limit of this is. This is continuous everywhere, so it's certainly continuous at whatever the limit of this is. And since that's the case, then I can go ahead and state that if I wanted to do, again, the limit of the cosine of 2 over n, this is equivalent to doing the cosine of, and I can kind of move the limit to the inside. Once I have this, I can see that the limit of 2 over n as n goes towards infinity, that's just going to turn into 0. Oh, and what's the cosine of 0? Well, that's 1. So here I have a limit of 1. And notice I've calculated the limit here. I didn't even have to convert to any sort of matching function. If I had this kind of composition of a sequence inside of another function, a limit can bypass that function, provided it's a continuous function.